Y. Uh, Sometimes this frame is always you will see at some joint, but it may be also possible that this frame is available at some other corner or in the world, somewhere in the world, right? And from that location you are seeing your mechanism. So from that location you are seeing the points or joints of all the uh, links of your mechanisms, and you're trying to tell what are the coordinates of those joints and those links, okay, and how your link is moving. So with respect to that world frame, you are trying to uh, uh, define your mechanism. Okay, so here you are seeing a mechanism reference frame that is X and Y, and so location there is a location of point P on the frame. So this is your link, and there is a point P on that link which is actually doing some task. So we are trying to define that location of P with respect to your world frame, and that P is making angle theta in vector form. So if you see from this position that P, so it will be in vector, and that vector is making angle theta. The direction is angle theta from with respect to x-axis. So if I ask you in terms of coordinate, what is the position of P in x and y? So you can say that it is rxp or ryp in y, and or in terms of point position of point. So you can write it px and py. So px here is rp cos theta. This is cos theta. So all simple trigonometric function you have to use. And similarly for y, you can write rp sine theta, right? So it's very simple. I think it's basic for you. And yeah. So in the next slide, now comes to linear displacement. So let's say you are at point P. Now your mechanisms has moved and it reached to new location, that is P dash. Okay, and you want to determine what is the position difference in terms of coordinate. What is the position difference over there? So you will have some position over here that is P dash, and some position at P, new location, means from old position P to new location P dash. So you want to determine that. So from new location, let's say it is some x1 and px2, okay, and this is some, sorry, py1, and this is some px2 and py2, this p. Okay, so the difference of that will give you the coordinate of your new location. That position is determined by px minus py in terms of x and y coordinates. Similarly, you can find out the linear displacement. So actually how much displacement has been happened. That was the difference. Now you can determine the linear displacement, and that simple trigonometric function, or so that px squared plus py squared, you just have to square them up and you will get the displacement, right? Now similarly you can find out the angular displacement. So previously maybe it was at some angle theta 3, and now it has moved to an angle, let's say theta 3 dash. So new minus the old one, you will get the change in the angle. What change in the angle is happened if your link has moved, right? Okay. Now this is just basic. I would like to cover before we are going move to 4-bar mechanisms. So now we are going to talk about 4-bar mechanisms, which is uh, you can say a kind of a base for your kinematics of mechanisms, right? So it simplifies many things, and it tries to help you understand many mechanisms. And this is the simplest mechanisms that people try to solve, and take a base of it first to understand many mechanisms in future, right? So we'll talk about it, and we'll see how this mechanism works. So this is the simplest and more uh, common linkages mechanisms, or 4-bar mechanism linkages. So it is a combination of 4 links, one being designated as a frame. And so frame will be your base, which will be fixed, and it will be connected by further 2 points, and you will have 2 more links from there, which will be connected by 2 more joints and 1 link. Okay. So because it is encountered so often in your daily life as well, so that's why we are going to discuss it first. Okay. So maybe if you in your first slide or first lecture that we had, I have shown you a mechanism for an automotive window wiper, right? So that window wiper is actually a 4-bar mechanism, if you remember, right? And yeah, so here is your window wiper. It's a rear window wiper or front window, anything you can say. So it is actually 4-bar mechanism. So what 4 bars you have? This is your first link. This is your second link. This is your this is fixed. One link is fixed. That's first link, then second link, then third link, and this is your fourth link on which you are actually having motion. Okay, so you just draw the line diagram of it. So this is your joint 1, and this is your link 1 as well for fixed. Okay, so this fixed position, this one and this one will be considered as link 1. Okay, so this is your fixed and this is also your fixed. Then this is your link 2, this is your link 3, and this whole complete structure that is forming here. Okay, this is your link 4. Okay, so this is your link 4. So it's a 4-bar mechanism which works for rear window wiper in your cars. It's most commonly used. So this is a very good example to understand 4-bar mechanism in start, right? Yeah. So what you actually have? So you have link 1 over here, which is ground fixed. Link 2, you will see it is a crank. Okay. So when you are actually giving input over here, you will have a motor connected over here. Okay. And that is rotating and it is giving input. So because of that input, this link 2 will completely rotate in a circle. And that's why we call it as crank. So it's a side link which revolves relative to the frame. Okay. So around the frame, it will rotate. Then you have a coupler. So coupler is nothing but it is connecting this rotating link with another last link. That's your fourth link. And that's link 3 is your coupler. So any link that couples or join two other links, it's called coupler. And then we have a rocker. Okay, so any link which does not revolve. So when you will see this mechanism, you will see it is not completely rotating. It's actually making some oscillatory motion. So it will go till here and then it stops and then it will come back over here, stops and come back over. So it's like oscillate. Okay. And so that's why it's called as rocker. So I already explained these two terms before also in last lecture. So crank, which always do full rotation, rocker, which is not able to complete its rotation. It may be possible out of 360 degree, it may be completing 350 degree or 270 degree, but it will never complete full rotation. And if it is not completing full rotation, that is rocker. Right. So these are some basics for that. Now let's see how you will find the degree of freedom for this. So, or you can say the mobility, how you will see this mobility in which, so most of the times, almost always, you will see that 4-bar mechanisms is used whenever you are using 4-bar mechanism, you are getting 1 degree of freedom as output. Okay, means only one directional output you will get. For example, here you're giving input as a crank rotation, but output you are getting as a rocker mechanism, right? Oscillatory motion you are getting as an output. So how we will determine that? So first we will see number of joints. How many number of number of links? So we have 4 number of links over here, n is equal to 4. Joints, so pin joints we are seeing here 1, 2, 3, and 4. So 4 pin joints we have over here. 1, 2, 3, and 4. So this is 4. And higher joints we don't have any because we don't have any geared or cam follower mechanisms over here. Okay, so that's why it is 0. Now we'll put these terms in this formula. So you have 3n minus 1 minus 2j minus j. So this is 0. So 3 into 4 minus 1 minus 2 into 4, and you will get it as 1. Correct? So this is your 1 degree of freedom that you are getting for this lane, this one directional motion you will be having. Yeah, so this is very simple. And yeah, so it's very simple. So this we call it as mobility of 4-bar mechanisms, okay, which consist of 4 joints, 4 links, and you will get 1 degree of freedom over there. So because 4-bar mechanisms has 1 degree of freedom, it is constrained, okay, or fully operated with one driver. It means at one side you have to give input, and other side you will get the output in some kind of motion. So the Viper system that you have seen now is actually activated by a single DC motor at your joint 1, is just before the link 2. Okay, that fixed position you will have a DC motor which will be giving the input as power. Of course, the link that is unable to move is referred to as frame, which is your 1. Okay, so that is fixed frame which is not able to move, and because of that only you are able to achieve this motion. So typically the pivoted link that is connected to the driver or power source is called as input link. Okay, and the other pivoted link that is attached to the frame is designated as output link or follower. So the coupler or connecting arm, which is your link 3, which actually couples the motion of the input link to the output link. Right. So in very simple terms, we have understand this all of this, and these 4-bar mechanisms is actually works on your Grasshoff's criteria. Okay, so there you will have 4 links. So out of those 4 links, you will have 1 link which is the shortest. Okay, you will have 1 link which is longest. You will have 1 link which is means other 2 links you will have P and Q, which are intermediary link. So P is here is one intermediary link and Q is other intermediate link. Okay. Now fixing any of these links will create different kind of motions and different kind of mechanisms. Okay. And this 4-bar linkages will have 1 full rotation. Okay. So you have 4 links. Okay. So there you have 4 links. And out of these 4 links, in any of the 1 link, you will always have rotation, or at least any of the 1 link. You can have rotation at other 2 links as well, but at least 1 link rotation you will have if shortest plus longest link is less than is equal to other 2 intermediary link. Okay, so the summation of length of shortest plus length of longest link, if it is always equal or less than equal to sum of P and Q, other 2 intermediate links, then you will always have 1 full rotation in your mechanism. Okay, so this is one thing to understand. So here I am showing you one example. So this is a double crank. Okay, so it is how it works. So your shortest and the longest link is smaller than P plus Q over here, and you're seeing that at least 2 circular motion that you're seeing over here, right? So another is crank rocker example. Here you will see only 1 link is rotating. So this is actually how your Viper works. Viper in your car, this is how it actually works. So here you are having input, and this is how it is doing this wiping in your windshield. Okay, Here also your shortest plus longest length is smaller than or equal to P plus Q. Then we will see this double rocker mechanism. But you will see that you are not getting any full rotation over here. And shortest plus longest length is actually bigger or larger than P plus Q. That's why you're not having full rotation. Okay. So there's one more condition means which we didn't see till now. So all these here you have S plus L is always smaller than P plus Q. Now you will have a condition where S plus L will be is equal to P plus Q. So in this condition, what will happen? You will form actually a parallelogram linkage. Okay. So this opposite links will always be equal. Okay. So this will be equal to this one and this will be equal to this one. So any smallest plus largest will be is equal to P plus Q, which will be always equal to smallest and largest link. Okay. So this is actually forming a parallelogram and yeah, so parallelogram also have some applications. So maybe you have seen a train wheel. I don't know whether you have trains. So train wheel actually move like this. So you will give input to one wheel, and because of this parallelogram, other wheel moves. Okay, so it transfers the motion to other wheels, and it moves. So let me just show you one example how this parallelogram will work. I have to share my screen again. So this is screen. Yes. So here you are seeing a 4-bar mechanism. This is a software called Mac Analyzer. And I'm just using this to explain you how different mechanisms work. Okay. So what I will do, you can see this link over here. So here this base link is L1, smallest link is L2, opposite side is L4, and this is L3. Don't worry about L5 and L6 for now. I made it 0 for now. Okay, just to show you 4 bars. So let's make 2 links of the same size. So I'm making L1 as 0.3 and L2 as 0.5. L3 as 0.3 and L4 as 0.5. Okay. So how it will move? It doesn't move. So I will just make it smaller. Let's make me 0.4 and this also 0.4 so that it would be visible. Yeah. So how it will move? You can see. So something is out of screen. I don't have mouse. Otherwise, I could have make it smaller. Okay. So this is your link is moving. Okay. So this is your parallelogram linkage. Okay. Let's move to our slide. Okay. So now let's take one example over here. So here you are seeing this is actually you can say you have seen a landing gear maybe in a flight or in any airplane. So this is that landing gear from that guide. So it's a nose wheel assembly. Okay, so we call it as nose wheel assembly, something like that it is. And we first made the kinematic diagram of it. So here you are seeing we have made the kinematic diagram. Okay, and so this is your point C, D. This is your link 3, this is link 4, this is link 2, and this fixed is link 1. Okay. So first we will determine what are the shortest, longest, and other two lengths. So shortest you are seeing here is 12 inches. Longest is 32 inches. P is 30 and other Q is 26. Okay. So when you will add them up, shortest plus longest and P plus Q, you will see you are getting 30 plus 26 over here. So that's 56 and other side is 44. Okay. So this is your mechanism. And so basically what happens when you have this mechanism, you will have at least one rotation, which is over there at smallest arm. So at the link number 2, you will have full rotation if you want. If you don't want, it's okay. It's up to you as well, whether you want full rotation or not, even though it is available. Okay. So now my question is whether what kind of mechanism it is. Will you call it as crank rocker, or will you call it as double crank or double rocker? What kind of mechanism it is? Anyone can answer? Is it crank rocker, double crank, or double rocker?
I think it's double rocker, sir.
No, it's not a double rocker. It's a crank rocker because here you will have full rotation. So this is your crank, okay, and this is your rocker, which will move in oscillatory motion. Let me do one thing. I will take these values in points and put in that Mac analyzer. So we have 12, 32, 30, and 26. Okay. 12, 32, 30, and 26. And we have fixed here this 32. 32 is fixed. Largest length is fixed. So I will just go to Mac analyzer. I will share my screen for the Mac analyzer. Okay. So we have link 1 as 12, link 2, link 1 we will consider as 32, link 2 is 12, link 3 is let's say 26, and link 4 is 32. Okay, so let's see what kind of motion you are getting here. So this link 1 starts moving. See, so this is completely rotating, it's crank, and this is only oscillating, this other link. Okay, and that's why it is crank rocker. So this is crank and this is rocker. Okay. Okay, so let's go back to our slides. Yeah. So this is your actually crank rocker mechanism. Okay. So this you have to identify what kind of mechanisms it will be. And so if you, so it's very simple. So if your frame is fixed, means if your frame is fixed, and the shortest link is your frame. so shortest link is fixed, then you will have double crank. And if your side link is fixed, then you will have crank rocker. And if your coupler, which is joining the other two links, that is fixed, then you will have double rocker. Okay. So this is the thing. And if both opposite sides are equal, then you will have change point mechanisms, or you can say parallelogram mechanism. And in any case, if S plus L is greater than P plus Q, then in that case, you will have triple rocker mechanism. Okay, so in that triple rocker mechanisms, you will not have any, what do you say, rotary motion over there, or crank motion over there. Okay. So now let's see this 4-bar mechanisms in terms of your vector geometry, or in terms of the frames. So here you are seeing this is your 4-bar mechanism. Okay, so this mechanism is O, A, B, O, C, and you have the fixed frame W. Okay, and there's another frame which is placed on point O, which is named as F. Okay, theta is your input. Okay, so let's say you attached a motor over here, and from that you are giving an input. So theta is your input. So how much angle of rotation you are giving over here in the motor, accordingly you will get motion over here. And psi is your output angle. Okay, so this is your output angle, which is you're getting as output psi. So this fixed frame length is G. The smallest is A, coupler is H, and other link is B. Right? Okay, so this is your this general description for this 4-bar mechanisms. Now, in vector loop, in terms of vector loop, how you will define these points O, A, B, or C? Any main concerns are our A and B, because C and O are fixed, right? So how you will define that? So uh, so what I'm showing you here is we are defining the moving point, moving pivot B. Okay, so we are moving pivot B. So how you will define it? So we can write it as A is equal to B minus A. Sorry, A plus B minus A. B minus A is nothing but it's H, and A's position is this. So you know the position of A plus B minus H means B minus A, whatever position is there, you will reach at the B. Okay, so this is from this location. Now from the C side, you will see C. Let me just draw it. So here you have your O, this is your A, this is your B, and this is your C. So this is, you will have, for A you will have some coordinate of XA and YA, right? And for B you will have some coordinate of XB or by B. Okay, so what is the location of B? Okay, means what you're pivoting B, you are just trying to see B from there. So A plus whatever this link is showing you, means how you reach over there B, that will give you that pivot B. Similarly for C, so C plus B minus C, this link. Okay, this link, it will be equal, because just we are trying to see it from A side and B, C side, two sides we are trying to see it. Okay, now, so what is the vector for A? So A, we can write it as A cos theta and A sin theta in Y. So A cos theta is in X, A sin theta is in Y. B minus A, so it's H. Okay, so H cos phi, this is your phi, this is angle it is making for with respect to horizontal plane. So h cos phi in x and h sin phi in y. Okay. C we can write it as g comma 0 because it's in x plane. Your coordinate is here, means your frame is here. So x is g and y is 0. Okay. And plus b minus c is equal to b cos psi and b sin psi, right here. So these are nothing but it's your coordinate in x and y in vector form. Okay. So like that we can write it. Now, for a given input angle of theta, okay, so for a given input angle of theta, a known value of psi, the loop vector equation is solved. Okay, so you will know the input value angle theta, and you will know psi, and loop vector equation you will solve to determine the coupler angle phi. This coupler angle you will determine from there. So how you will do that? So you will solve this equation, and you will find this phi is equal to arc tan b sin psi minus a sin theta divided by g plus b cos psi minus a cos theta. Okay. So this phi is actually defined in terms of psi and theta, which are known. So when you will know these values, you can always be able to determine psi. And with this psi, what you are actually going to achieve, you are actually going to achieve, and you will know in what kind of motion it is moving. You will be able to determine the equation of motion, means what curve or what path it will take while it is working. Okay, so we are using arc tan over here. It's because you will have two position of this phi. One is positive and one is negative, and that's why we are calling it here as arc tan. And that's also because if you see, for each position, you are defining it with respect to x and y, and it's in cos theta and sin theta. So for both cos theta and sin theta, you will get different value for the same theta. And but you want a unique value, and that to unique value will be in terms of phi, but you will get two values, one positive and one negative. It's 180 minus. So it's one value is phi and other value is phi minus phi. So like that. Okay, so 180 degree is just opposite to it. Then let's see the algebraic analysis, how we'll see the algebraic analysis of it. So algebraic analysis is done by formulating a constraint equation over here. Okay, so a constraint equation is important if you want to do computational kinematics. Okay, if you want to do computational kinematics, this constraint equation is very necessary to do. So that you can determine all the parameters for your mechanism. So constraint equation of 4-bar mechanisms is obtained from the distance h. Means our main concerns are A and B because O and C are fixed. Okay. So of point A and B, which will always be constant because it's a fixed rigid link. Just your point A and B is moving, that you should know. So here we are doing the algebraic analysis for this. So for A, we can write vector in this form, right? And for B, we can write vector in this form. So it's G plus 0 plus this part. So it's B cos psi plus B sin phi. Okay. So this is how we are defining uh, your A and B. And it is with respect to this frame F. Okay. So with respect to frame F, we are defining A and B in terms of vector. So now your constraint equation will form through B minus A into B minus A minus H square. That will be equal to 0. So it's like that. Okay. So what will be that? So basically you just have to open it B in terms of your trigonometric functions. You just have to enter all the values in terms of A, B, A, G, B and H. Okay. And in terms of cos psi and sin psi and theta. All these things you will enter it over here. And when you will actually solve it, you will it should be, you will equate it to 0. Okay. So this is how you will do algebraic analysis. So was the equation that you got, right? And now what we'll do, we have this cos psi and sin psi, and we will uh, replace it uh, uh, with a tangent of half angle. Okay, so that it will be easy to solve. So um, how we will do it? So like sine phi, you can write it as 2 tan alpha by 2 plus 1 plus tan square alpha by 2, and cos alpha we can write it like this. So similarly you will do it over here. Okay, so because you want to find psi, you will replace it with the tangent of half angle. Okay, so this is how you will do the algebraic analysis. And now let's see one assignment or one example over here, which we'll do it in the class. So here you are seeing an example of uh, this a toggle clamp. So this toggle clamp is actually used for securing a workpiece during a machining operation. Let's say you are doing some machining operation on planing machine or shaping machine, or let's say a milling machine. There you can use this toggle clamp, okay, to hold the workpiece. So what we are doing here, we want to determine the angular displacement. We want to determine the angular displacement of handle, how your handle will move in angular displacement, and hence the handle must be displaced in order to lift the clamp 30-degree clockwise. Okay, so right now in this position your clamp is locked, it is at 90-degree, and you want to move this clamp 30-degree clockwise. So what is the clockwise direction? This is the clockwise direction. So if you move this 30-degree clockwise, this angle will become 60-degree. So this is what we want to do, and I want to determine what angle you will have it over here. Okay, so this is what we want to determine the angular displacement of the handle. Okay, so let's do it. First, we will draw the kinematic diagram of this example. So this is your kinematic diagram. So here your A and D are fixed. Let's first see this kinematic diagram for 10 seconds. I will go back there again and explain it to you how this kinematic diagram has been made. Okay, take 5-10 seconds, see how it is made. Just for the explanation, this is your coupler. This is your coupler. This is your link for the handle. This is the other side from where you are actually holding uh, the workpiece. Okay, so let's go back. So this is your one link. Okay, this is your lever. This is how it is forming. This is another link, and this is your fixed frame. Okay, so like that it is forming this kinematic diagram. So this is your what you say, link 1, not 4. This is your link 2, this is your link 3, and this is your link 4. Correct? How many joints you have? 4 joints. 1, 2, 3, 4. So this is 4 bar mechanisms. Okay. Okay, so this is the actual position now your mechanisms is. This is the original position, and I am giving some link lengths over here, that's 25, 12, 20, and 15. Okay. What I actually want, so I want to pull my lever in such a way so that you will have some angular displacement over here. Okay, and that angular displacement will actually change this angle from 90 to 60. So like this you will have. Okay, so this position you want. So this is the your displaced configuration. So what's actually happening? Previously you were at 90-degree, and your lever was placed at 96.1-degree. This angle is 96.1-degree. Okay, so this is 96.1-degree, and when you pull the lever so that this part becomes 60-degree, So this angle becomes 133.3. So this angles become here 133.3 degrees. Okay. So either you find this angle or this angle. So actually this is your what you say, angular displacement of actually lever. From here also you can measure it, or this angle also you can measure it if you want. Okay, but it is inside the mechanism, so that we will take this one. And so any one mechanisms you can find. So once you know these two, you can find other two as well. Okay, so by the law of 360 degrees you can find it. So once you know this one, opposite angles will create angle of 180 degree. So like that you will find the opposite one, and next this one you can also find. Okay, so this is your final coupler angle that you will form. Right. And here you can see what is the shortest link. It is 12. Longest is 25. Okay, so this is your shortest plus longest. And what about P and Q? So P is 20 plus 15. So this will comes out to be your 37. And here you will have your what you say, 35. Okay, so here you are seeing that S plus L now becomes bigger than 30, means P plus Q. It is a 4-bar mechanisms, but it is not, means in this mechanisms you will not have full rotation of any link. You will not get full rotation of any link. So what we will do, let's check this example in our analyzer software. That will be good. So we have uh, let me just share my screen for mechanizer. So what we actually have, so we have 12, 25, 20 and 15. Okay, so 25 is here, 12, 20 and 15. So let's try it. Where is your mechanizer? Yeah, here. So we have a fixed length as 25. Then this is your 12 L2. This is 20. This is 15. Yeah, this is 20, and then your other is 15. This is your 50. Okay, so let's see this mechanism working. See, here it is locking, and it doesn't complete the full rotation. Now again it will lock over here because of this link. It will not be able to complete the full rotation, and then it will return. So let me just make it a bit fast. Okay, so this is how it is doing, and this mechanism will actually lock at some point of time. Okay, so you will not have to complete the full rotation over here. If you do it, your mechanism will lock, and it will be difficult to come back from there. Okay, so let's go back to our slide. Yeah, so I hope you understand this thing. Now next assignment is your parallelogram assignment. So basically you have to do what you have to do. A point Q moves from A to B. Okay, along the coupler link 3, while link 2 rotates from 60 to 150 degree. Okay, so this is your link 2. Currently it is 60 degree and then it moves to 150 degree. I'm asking find the linear displacement of point Q. So point Q you can place anywhere over here on the link AB, and I want the linear displacement of point Q. So link 1 and link 3, this one and link 3 you can consider equal, that's equal to 4, and link 2 and link 4 is equal to 2. Okay, so that you can try in home. So what will be the linear displacement of point Q? Okay, so this is your assignment. It's very simple. You just have to use the vector form and you can find it very easily. Okay, I will keep the deadline for this assignment as 6 p.m. today. Okay. Okay, now uh, we will see another term that's called limiting position in 4-bar mechanism. So as I shown you there also, uh, sometimes you see that your mechanism is locked. So the configuration of mechanism that place one of the follower link in an extreme location. Okay, so that's called limiting position. Beyond that, it cannot go. So that's the limit of it. So when you put the mechanisms that place one of the follower link in extreme location, that's called limiting position. Okay, so in this position, the mechanism is blocked, and hence this position is also called a singularity, because you have restricted one of the degree of freedom, or you're not able to do any task over there because of the blockage of the mechanism. So that's called singularity. So for example, over here you can see this two links are now in same line and it is blocked. Okay, uh, so that's an example of crank rocker mechanism. So in this limiting position, you will have one minimum limiting position and maximum limiting position. So what is the minimum limiting position? So in minimum limiting position, you will have this B in the opposite side. Okay, this link will be here from C to B dash. So that's your minimum position or minimum angle that you are forming over here, this one. Okay, so that cos theta min, you can find it from here. So h minus b square, h minus b square minus a square minus g square divided by 2ag. Similarly, you can find the maximum angle which is over here in full extension, cos theta max h plus b square minus a square minus g square by 2ag. Okay, so this is how you can find the minimum limiting position and maximum limiting position for your link, follow link. Okay. Okay, so this is your next assignment. So in this assignment, what you have to do, uh, so a linkage is used to operate the water nozzle and automatic car wash. So what you have to do, you have to determine the limiting position of the mechanisms that place the nozzle in extreme position. Okay, so you have to find the limiting positions of the mechanisms that place the nozzle in extreme position. Okay, so this is your assignment that you also have to use. So 2 assignments will be there. I will soon after this lecture upload these 2 assignments for you. Yeah, so for this assignment as well, by 6 p.m. today, you have to submit it, because these are very simple. Maybe it will take 15-20 minutes for both of them to solve you. Okay, so in 4-bar mechanisms, now there is another terms that called as transmission angle. So what is transmission angle? So here, this is your crank, this is your rocker, and this is your coupler. So between your coupler and follower, one angle will form that we call it as transmission angle. Okay, so transmission angle gamma, which I am representing here as gamma, quantifies the force transmission through a linkage. So how you're transmitting the force? Through this coupler to this follower. Okay. So pole transmission through a linkage. So minimum transmission angle gamma min. When it will be gamma min? So when you will have something like this posture, you will have gamma minimum, and so that will be cos inverse, and this L3 square plus L4 square minus L1 minus L2 square divided by 2 L3 L4. L1 L2 L3 L4 is nothing but it's the link length. So this is your L3, this is your L2, and this is your L4. Okay. So all that you have to just enter. And maximum transmission angle is nothing but gamma max, which is this one. Okay. And so whatever is the maximum angle that is forming over there during this rotation, that you will take as gamma max, and that's cos inverse L3 square plus L4 square minus L1 plus L2. The only change is L plus L2 there was minus, divided by 2 L3 L4. Okay. So this is how you can find the transmission angle. So it's very basic geometry or trigonometric function. So you just have to use to find this gamma min and gamma max. Okay, so transmission angle that you're seeing, this gamma, is actually neither maximum nor minimum. Okay, so it's always changing. So calculate uh, what we'll do, we will calculate this BD. Actually, this thing BD is actually defining your gamma. So we will calculate BD. So BD is equal to what? L1 square plus L2 square minus 2 L1 L2 cos theta 2. How it is forming? So BD is this. Okay. So this is your triangle. This is your L1. This is your L2. I am trying to find BD. So BD is nothing but L1 square plus L2 square minus 2 L1 L2 into cos theta 2. I hope you know this formula. So with that, we can find BD. And from there, uh, you can find the transmission angle gamma. So here you are finding the maximum and minimum. But if your transmission angle is neither maximum nor minimum, means you want to find it something in between. Okay. So that you can find it from there. You will just find the equation of BD. And from there, means just by using that equation, you can find gamma. So gamma is nothing but cos inverse L3 square plus L4 square minus BD square divided by 2 L3 L4. So BD is nothing but which we are using before as well. So we were using BD over there as well. So BD was this and this before. What is this? Means for minimum it was B double dash D, and for maximum it was B dash D. So that's nothing but L1 minus L2. But in this case, it cannot be L1 minus L2. So that's why we have to use this BD. Okay. So like that, you can find any angle of gamma, any transmission angle intermediate between maximum and minimum of gamma. Okay. Yeah. So now there's one more thing, coupler curve. So what coupler curve is? So you have 4-bar mechanisms, which was like this. Sorry. So you had something like this. You didn't have any coupler over there. So one link, single link, 3 link, and one fixed link. Like that you had. But one link you have extended something like this. And that point you are considering, let's say you have attached a pan over here. Okay, or a point which are plotting something. Okay. So that is coupler which is making a curve. Okay, so this link is nothing but a coupler which is coupling your uh, this input link with the follower link, and that's why it is making a coupler curve. So the function of mechanism is to guide a part to move along some particular path. So if you put a tool or something or a pan over here, it will follow a particular path during its motion. Okay, so this path is called as trajectory. And the trajectory traced by any point on this coupler is called as coupler curve. Let's see an example of it. So sorry, let's see one example of it over here. Where is our mechanizer? Here. So we'll see one example over here. I will just make a simple. So this is a coupler, okay, and when I will move it, so this L3 and L5 which I have shown you there in the previously. So this is actually L5 and L6. This is actually making your coupler, but otherwise your link should be like this straight. Okay, so let's see it. So this is how it is making a curve. Okay, so even if you are repeating this motion for number of times, you will get the same. Okay, so this is your coupler curve. Okay, let's go back to our slide. Were you able to see that screen? Because it is showing that video sharing has been paused. Let me show the screen. Okay, so I think you missed that part because the screen was not sharing. So we can see it here again. So this was your 4-bar mechanism, and this is your coupler, which is further extended by L5 and L6. Okay, and at the end of it, we have fixed let's say a pen to make a curve, or you can also put a tool to make cut something or do something or do some else extra task, whatever you want from it. Okay, so when we will do the forward kinematics and see how this point is moving or making a curve, you can see it from there. See, so this is making a curve, and this is actually your coupler curve. Okay, so let's go back to our slide. So here you're seeing this coupler curve. How you will find this coupler curve? What will be the equation of this coupler curve? How you will found it? Means what kind of trajectory it will form? So that we are going to see here. So what we are doing, this is your 4-bar link mechanisms. This is your fixed link. This is your link 1, 2, link 3, link 2, link 3, link and 4. So R, C, and S. So this point A is nothing but I'm defining as X dash Y dash with respect to this frame X and Y, which is at region O, OA. Okay, from here. So with respect to this frame, I'm defining all these coordinates. So this A is nothing but X dash Y dash. B is your X double dash Y double dash here. And your M is this one is your XY, which is actually okay. So this is nothing but your coordinates for point A, B, and coupler point M. So X dash we can write it as X minus A cos, B cos theta. X dash we can write it as B minus, X minus, what is X? X is still here. Somewhere maybe here. So X minus B cos theta. Okay. So B is what? So B cos theta will form here. So from X, when you will remove B cos theta, this part, you will get this part. Okay. So X dash is equal to X minus B cos theta. Similarly, Y dash is equal to Y minus B sin theta. Similarly, for this, X dash, X minus A cos theta plus gamma, and Y double dash is equal to Y minus A sin theta plus gamma. Right. Okay. So Very simple, very simple geometric function. All you just have to use and trigonometric functions to find out all these things. And since A and B describes circles, what A and B are doing, they are describing a circle or arc of circles. Even though if they A and B are not able to complete full circle, at least they are making some arc of the circle, right? So what those arc or full circle, they will have the equation of circle, right? Circle equation will be there about center OA and OB. So what will be those equations? So for R, this part R OA, x dash square plus y dash square is equal to R square. Okay, so R square is nothing but it's the radius over here. You remember, right? A square plus B square is equal to radius square. So that's the equation of circle. The same I am using over here. X dash square plus y dash square is equal to R square. Now for this one, x double dash y double dash, x double dash minus P. Why minus P? Because x double dash is defined over here with respect to this point, and you have to subtract minus P from there because your circle is moving with respect to this point. So you need x from here. This x you need, this one. Y will be same. So that's why y double dash square is equal to s square. Okay. Okay, so these are the two equations for the circle that your A and B are making. Now what we will do, we will take this x dash square and y x double dash square from here. So we will take these values. So substitute the values of x dash, y dash, x double dash and y double dash from there. And we will substitute it, means these values, we will substitute over here in this equation. So you will get x minus b cos theta square plus y minus b sin theta square is equal to r square. X minus a cos theta plus gamma minus p square plus y minus a sin theta plus gamma square is equal to s square. So these are the two equations that you will get. So you will just substitute these values from here to here in these equations. Okay, and you're getting this. Okay, so by application of trigonometric identities, what we will do, we'll take out x cos theta plus y sin theta and is equal to x square plus y square plus b square minus r square divided by 2b, right? So this is what you will get. So when you will solve it with trigonometric identities, you will get this one. So x minus p cos gamma plus y sin gamma into cos theta minus x minus p sin gamma minus y cos gamma into sin theta is equal to x minus p square plus y square plus a square minus s square divided by 2a, right? So what we will do now, we will try to eliminate theta from there. And so for elimination of theta from the two equations, we have general coupler curve. Okay, so when we will eliminate theta, we will get the general coupler curve. So how you will eliminate theta? So theta is nothing but is this. Okay, and we already alpha because your coupler angle is fixed. This beta is also you know, and this gamma is also known. In your equation, you just basically have to replace your theta with the known values of alpha, beta, and gamma. So you have to define your theta in such a way that it is defined in terms of alpha, beta, and gamma, and you just have to enter it over there in the equation. So here you are seeing I am defining the same equation now again. Sin alpha x minus p sin gamma minus y cos gamma into x square plus y square plus b square minus r square plus by sin beta over here. Same, x minus p square plus y square plus a square minus a square, the whole square, plus sin alpha x minus p cos gamma plus y minus sin gamma x minus x plus y square plus b square minus I square, r square. And similarly this part, and here you will have 4k square sin square alpha sin square beta sin square gamma and this part. So here you will see that there is no term of theta. All things are defined now in the known values of alpha, beta, and gamma. So if you will replace it with the known values, you will get, when you will solve this equation, you will get the curve for your coupler curve, basically, right? So like this, you will be able to find the equation. So you can try it in MATLAB if you want, or I have shown you one Mechanalyzer soft and example as well, how it can form a curve, right? So this was the basic maths behind it, how this equation is forming and how that curve is forming over there, right? Now let's move to slider crank mechanism. Okay, so this is also kind of a mechanism which is very widely used. Okay, and what do I say about this mechanism? So uh, so this mechanism is like so in the mechanism you will have one slider. So in place of one fixed part, you will have a slider over on the fixed part. So what I mean, so you will have 4-bar linkages with 4 revolute joints. It's same. It will form a quadrilateral. It's also same like before. But 4-bar linkages that has prismatic joints, it forms a triangle actually. Okay. So other links will become something like this. So this was your 4-bar linkages. Okay. So you had 4 revolute joints and it was forming a quadrilateral. But in this, what you will have, one link you will replace by this sliding link. Okay. So here you will have crank rotation, slider crank. So why it is called slider crank? Because you have a crank and one slider as a link. Okay. So that will give you translation motion, or you call it as prismatic motion. So the slider will rotate and this will move forward and backward. Best example for this is piston cylinder arrangement. Piston cylinder in your engine, maybe in two-wheeler or four-wheeler. Okay. So this is very good example for that. This is double slider linkage. Okay. So now what happens? This is your link 1. Fixed link is, so how you will define the links over here? One link means fixed one, second link, third link, fourth link. Okay. Here also you will have a third link is this slider and fourth link is this. Sliders, how many, whatever number of sliders are there, each slider you will consider different link. Okay. Only fixed link you will consider as one, as a base. Okay. So here also you will have 4-bar linkages, but it is double slider linkage now. So let's see the slider crank mechanism. So here you are seeing the frames for slider crank. So this is your frame for slider crank. So it's defined all in world frame. Okay, so the frame is moved to here at 0, 0. And slider movements S can be input or output. So this slider movement, it can be both input as well as output over here. So if you are giving it as input, this part will rotate. If you're giving it as output, means this part should rotate as an input. Okay. Theta is the rotation of the crank over here. In all the places you will see, this is the theta, which is rotation angle. Yeah. So this is also one way of representing the slider crank mechanism. So this is your link 1, link 1, link. This is your link 3 and link 4. So this is how you will represents. So this slider is link 4. Okay. So joint over here is not a revolute, it's a prismatic joint. Okay. So in this kind of example, The fixed frame W is placed onto O, okay, which is named as frame F, and theta is the input crank. Okay, you will just rotate theta, and this B, your slider link, will translate from there to here. Okay, so in loop vector, how we'll see it? So the loop vector form is used to find the coupler angle phi. What is the coupler angle phi which is forming over here? It is the angle phi which is forming here. That's I want to find. So A cos theta, A write it as A cos theta and A sin theta, and B is A H. We can write it as H and phi. And B alone we can write it as S. So this X distance is S and Y is E. Right. So S and E. Right. So when you will solve to find phi, this coupler angle phi, it will be like arc 10, means you will always get two values over here, phi and pi minus phi. Okay, so two values, that's why arc 10, E minus A sin theta divided by S minus A cos theta. Okay, so this is the value of a coupler angle that you can get from here. Now let's do the algebraic analysis for it. So in algebraic analysis, it is done by formulating a constraint equation basically, right? So constraint equation is used to find the position of B. If you're giving some input at O, means in theta, what will be the position of B with respect to that input? So what we can do, let's write the constraint equation. A we already know is A cos theta, A sin theta, and B is S and E. So we are defining with respect to their frame O. So constraint equation write it as B minus A into B minus A minus H square is equal to 0. So we just have to equate it to 0. That's constraint. Just for open this B and A in the form of their trigonometric values in form of X and Y. Okay, and just put it over here and equate it to 0. And you will be able to find the constraint equation for this. Okay, so this is how you will do the algebraic analysis for it. Now here you have your assignment. So for the slider crank part, so the handle you are seeing here, what is actually doing? It's a stamping mechanism that you are seeing. So the handle is rotated 15-degree clockwise. This handle right now it is at 50 degree. The handle will rotate 15-degree clockwise. Determine the resulting displacement of the stamp. You want to determine the resulting displacement of the clamp, how much displacement you have it over here. Okay, and the linear displacement of the handle end and the linear displacement of the handle end. So let's say it was here, how much linear displacement has been happened to change this value by 15 degrees. So this is what you have to find, and you can try it in home. Okay, now in slide crank as well you will have limiting position. Okay, so what will be the limiting position? So when your slider is at the maximum side where it can reach, there you will have what you say maximum limit, and if it is at the at over here C dash, you will have the minimum limit. So you will have sine theta min and sine theta max. Two thetas it will be formed. So minimum limiting position here is E divided by H minus A. Okay, so this is the position where you will have this uh, sine theta. Okay. So this is your theta mechanism, and similarly you will have maximum limiting position sine theta max E divided by H plus A. Okay, so A is nothing but this is your H, coupler link. Okay, so E divided by H plus A. So that will give you the sine theta max. Okay, now transmission angle gamma. So transmission angle will always form with coupler link to the follower link. So follower link is C. So this is your transmission angle gamma. So here you will get gamma min and here you will get gamma max. Okay. So that gamma min is cos inverse L1 plus L2 by L3 and gamma max is cos inverse L1 minus L2 by L3. Simple triangle it is forming, so you can easily find it. Now let's see this kind of mechanism where you have a slider like this in the link. It's like a piston cylinder arrangement, or you can say some kind of a hydraulic cylinder arrangement it is. Maybe you have seen the hydraulic cylinders in the dumper trucks which comes and open and through the things from the slides. So first we will have to make a vector loop which is a plus b minus a is equal to b. So there a plus b minus a is equal to b. So right, so that will be the b. So a is a cos theta by a sin theta, and b minus a we can write it as s cos phi and s sin phi. Right, so this is your s. It's not h, it's s. Okay, and b we can write it as bx and by in form of means x and y from this frame O. Okay. So once the slider length S is known, once you know this S length, you can solve phi, right? But S length will be changing. Why it is changing? Because it is a piston cylinder arrangement. So whenever you are having some rotation, this piston will go either in or out. So if it is going in, the S will be small. If it is going out, S will be large. So like that, it will change. So what we'll do, we'll make a constraint equation or algebraic analysis now here again. So this is how we will get phi in from vector loop, and algebraic analysis we'll do here. It's similar. A and B, you just have to enter B and A in the form of the given values, s square plus 2ab, x cos theta plus 2ab, y sin theta minus all this, and you got the constraint equation. So just remember previously when we had this example, we had this constraint equation, right? So this S is this one, okay? This change of slider position from origin, and you had a coupler length H there, okay? But in this example, you don't have a coupler length H in the equation, okay? So coupler and fourth link is itself in the same place, more here itself. Okay, now there is one more mechanism, that is inverted slider crank. So what we do here, we just invert the slider crank mechanism. So an inverted slider crank mechanism is shown here in the picture, which OA, and so here OA is 4, okay, and BC is 6. Okay, BC is 6. So the link OP, that link is at initial position now, and when it reaches its maximum input angle, find the minimum input angle. So we have to find the minimum input angle, and the link OP is rotated 50 degree from its initial position. So what will happen? Link OP is rotated 50 degree from its initial position. So let's say if it is 30, so it's rotated 50 and it reaches to 80 something. So just example, it's not actually that. Okay, and so when the link OP rotates 50 degree from its initial position, find the displacement of P and measure from point B. Okay. So we have to just find the displacement of P with respect to from point B. How much it is moved from point B, because your slider is moving on this BC link. Okay. So uh, this part we will see. So just a minute. Yeah. So this part we can see, and it's a kind of example that we can solve. So try this part in your home, and we will discuss this part in the next class, and then we will continue our class in the next lecture. Okay, that is on Monday. So try to do it, and so it will actually give you continuation from the next lecture, and it's kind of a revision that you will have first. But this is not an assignment. Just try it in by yourself, and we will see how we can solve this in next lecture. Okay. So you just have to find this vector loop or algebraic analysis you can do, and you can find these things that is asked over here. Okay, so and that's all for today. If you have any question, you can ask. You are welcome to ask it actually. Is there any question that you would like to ask?
Sir,
Yes.
I'm interested on knowing what is point of interest, sir. So in the last slides, there are one example of kinematic diagram which has point of interest.
Sorry, in which slide?
Uh, it's in the beginning, I think.
Okay, so you had a problem in
Ah, wait.
determining this one.
Yes, there are also another one with two point of interest, sir.
Okay, so here you have problem in understanding how kinematic diagram has been made.
Uh, I I want to ask about what is point of interest, sir.
Uh, Sorry, I don't understand you. Latifa, can you explain what he's trying to ask?
I think, and if you go down below,
Yes.
probably, I think this one, assignment one, I think.
Yeah.
I think point of interest, he's asking about what is point of interest. I'm trying to understand, I think it's here in the handle. Yeah, this at point X, he's writing it in the chat group.
Okay, so he's trying to ask what this device is actually doing.
So Abi, what are you trying to ask? What is point X? Is that what you mean?
Yes. What is point X and how do we determine if a kinematic diagram has a point of interest?
Okay. So I think if you go before this tip, the slide before this, yeah. I think here you have clamp arm in the left, and then you have handle in the right top. I think how will you draw the kinematic diagram? How will you simplify it? Do we have to draw the clamp as well, or do we have to draw the point of interest? I think that's what he wants to ask. For example, here you have a handle. Should we draw it as a triangle, or is it okay just if we draw it just lines?
No. So actually you have to draw it as a triangle because you have a handle over here. So when you see, let me just do it once. So, oh, this is not able to delete. Just
I think he's trying to ask how can we distinguish the link which has point of interest and not.
Okay, so you have to see, Miss. For example, here we have marked that it is handle. Here you have a clamp arm, and it's like a visual sense, or you can say a mix of visual sense and common sense. How this mechanism is working just by seeing the diagram, and that's why in your first year or second year of engineering you have this um, engineering drawing as a subject where you understand how engineering drawings looks like. So this is your joints, this is your, you really understand, right? And this is your fixed plane, that also you understand. And this joint and this joint is attached by fixed link. Okay, this is the link. And when you are seeing this handle, so it's actually not all the 3 points, this point and this point and this point where you will actually put your hand and hold this handle. Okay, so actually these are not at the same line, so that's why it is forming a triangle. Okay, so it will form something like this. Okay, so that's why it will form a triangle, something like this. And similarly clamp here, we made it like this because this is, will be the point of interest. And sorry, it will go till here and this will come till here. So here you will have another triangle. So when you push something over here at this end, you will get motion over here. So that's, so this here you have your input, and here you're getting the output for that in terms of another motion. Okay, so here you are doing some um, motion like this, some arc, and there you are getting output in the form of this translation motion like this. Okay, so when you will pull it, actually this part will go up and down. When it go up, you will attach this workpiece. So this is your workpiece. Okay, and then you will pull the lever back and it will attach it over here. So right now it is in locked position, and if you want to open it and remove the workpiece from there, then you have to change this angle to its full position, that is by 60 degree. You have to change this part, means this part you have to change 60 degrees so that it can be open. Okay, so like this, your handle over here is moving and it will be open. Latifa, I hope I cleared his doubt. If I
Yes.
understand, is this what he's asking?
Thank you, sir. I think
Okay.
it's clear.
And some other figure also you were asking, which one? This one? So this is your assignment. So what will be the input and output that you have to see? Okay. So what's actually happening here? You have a motor. So this motor will rotate this part and you will have rotation over here. Then you have this coupler link and you have this, what you say, another link, which is the follower. This is what it is happening here. Okay, so that's the automatic car wash spray. So you just have to figure out what it is actually doing to see what is the point of interest, what it actually want to do, that mechanism. Okay, because from the same mechanism, 4-bar linkage mechanisms, you can draw different kind of mechanisms itself. For example, let me show you some examples over here. I have shown you this 4-bar mechanism. So in 4-bar itself, you have many examples. For example, watt linkage. This is your watt linkage mechanism. So this is the simple one. Okay. So here your point of interest is this. So it's making some curve. Then you have this. So using the watt linkage, you can design any machine or some kind of motion where you want this kind of curve, or maybe not full curve. You want some position from, let's say, from here till here, so that you can see. Then you have cyber steps linkage. So in cyber steps linkage, what you have, let's see how it works. So you have point of interest in the middle. So you are actually making a curve from the center. Okay. And then you have Roberts linkage. So this we have already seen. So there you have curve over here. So it depends on if you change the link length, anything will change.
I think this is also, sorry, Dim. I think this is also point of interest.
Yes.
One example.
Yeah. So point of interest is depends on what you want from the mechanisms, and depends on that you can draw and you can have the mechanisms made from that forward linkages. You can change the link lengths and you can do it, right? So like that, there are many mechanisms which has been made on this. Uh, yeah, for example, this one. So your joint is still here, but you have extended the link to have a point of interest over here. And when you will run the mechanism, you will see how it is working. See, it's making a bell shape. So if you want some mechanism in which you always want to run your tool in this form only, like that you can do it. But for that, you have to understand what is vector loop, how you can run the equation of motion, how you can design the trajectory, how you can design the path. Okay. So all these things you should know. But here we are just covering the basic, and we are showing you with some examples so that you can understand different mechanisms properly. Right. And if I comes to slider crank mechanisms, this one, it's very simple. So in that, so you will see uh, many examples. So this is one example for slider crank mechanism. So even though it's sliding, but maybe you're not extracting output from this slider, you are extracting output from the coupler. Okay, so that is the couple curve that is forming over here. Similarly, Scott Russell is kind of a slider mechanism, and this you can see. So what you are forming here, it's a straight line. Okay, from this mechanism, you're forming a straight line. See, you have four wall linkages, and the point of interest is this: what do I actually want? I hope I have answered your question.
Yes, sir. Thank you.
Okay. So anything else? So Latifa, do you want to add something?
No, this is very good, very interesting. And will students get the chance to play with your interface or software next
Okay,
time?
so I will just tell them from where they can get it. So you're able to see my browser.
Yes.
Yes, sir.
Okay, so what you do in browser, you just search robo analyzer. Okay, robo analyzer .com. So you just basically have to go to roboanalyzer.com. So here you will get 2-3 softwares. Robo Analyzer is one of them. It's for robots. In that you have this VRM RTB, Teach Pendant, Mac Analyzer, and this is for dynamic read sim. Okay. So this click on Mac Analyzer. And in this Mac Analyzer, you can download this software. So here you will see different kind of kinematics linkages and mechanisms. You just download the latest version of whatever latest version of software is available. And if you want some tutorial for this software, there are some tutorials are also available there. So like your institute have a very good institute, IIT Delhi in India, and it is under Professor S.K. Saha, this software has been made. Okay. So it's for student and teaching purpose only. It's not for commercial purpose. So this is very good to understand various mechanisms and see how it is working. Okay. So please try and have a hand on this Mac Analyzer, and I hope it will help you understand various mechanisms and understand the subjects very easily. And in this, when you will go to this dynamics part, I don't know whether you are having inverse dynamics and forward dynamics. So that also you can cover it. Okay.